In this episode, we will talk about system prompt optimization with meta-learning. So, large language models, LLMs, they've just exploded, haven't they? Their abilities are, well, pretty remarkable across so many different things.
Absolutely. And how we talk to them, how we prompt them, that's become super critical to getting the most out of them.
Right, and a prompt isn't just one block of text, is it? I understand there are usually two key parts.
That's correct. You've got first the system prompt. Think of this as the sort of background instructions. It guides the LLM's general behavior, and ideally, it works across lots of different requests.
Okay, the foundational rules and the second part.
That's the user prompt. This one's much more specific. It's tailored to get a particular answer or action from the LLM for whatever task you have in mind right then.
Got it. System prompt for general guidance, user prompt for the specific task.
Precisely. And, for a long time, most of the research, the optimization effort, it's really focused heavily on tuning those user prompts for very specific jobs.
Right, like getting the perfect prompt for summarizing articles or another one for writing code.
Exactly. Loads of techniques have popped up for that. But this focus has meant, well, the system prompt, that potentially powerful, broadly useful set of instructions, it's been kind of overlooked.
Okay, so there's untapped potential there.
Huge potential. I mean, if we could really nail optimizing the system prompt, that could bring massive benefits across tons of different tasks, maybe even extending to completely new areas the model hasn't seen before.
Okay, let's dig into that. If everyone's been focusing on user prompts, what's the actual, core problem this new research is trying to solve? What gap are they targeting?
Well, the main challenge is figuring out how to automatically design system prompts that don't just work okay with some user prompts, but work really well with a whole variety of them.
Okay, robustness.
Robustness, exactly. And critically, these system prompts need to generalize. They need to be useful for totally new tasks the system wasn't specifically optimized for.
The generalization part. That sounds tricky.
It is. We're aiming for system prompts that aren't just A+ students on one type of test, but can provide a solid foundation for the LLM to handle lots of different challenges thrown at it via all sorts of user prompts.
It's like teaching fundamental principles instead of just memorizing answers for specific questions.
That's a great analogy. Exactly that. Teaching the core concepts so it can tackle unfamiliar problems effectively.
Makes total sense. So moving beyond just tweaking prompts for one task at a time, and instead finding this high-level guidance that works broadly, even for novel situations. How do you even start tackling something like that?
So this brings us to the idea of bi-level system prompt optimization. That's the term they use.
Bi-level. Okay, meaning two levels.
Exactly. The core idea is to optimize that system prompt so it's inherently robust to diverse user prompts and, crucially, transferable to unseen tasks. The bi-level part means there are two optimization processes happening, kind of interconnectedly.
Interconnected? How so?
Yeah.
What's happening at each level?
Okay, so at the higher level, the main goal is optimizing the system prompt itself. You want that prompt to generalize well across a whole bunch of different tasks.
Yeah.
Think of it as teaching the LLM a fundamental operating mode.
Right, the big picture rules.
Then, at the lower level, the focus is on optimizing the user prompts, but for specific individual tasks. So while the system prompt is being made better for general use, the user prompts are being fine-tuned for peak performance on their particular job.
Okay, I think I'm getting it. You're optimizing the general approach and the specific instructions at the same time, hoping they work well together. But how do you manage that interaction? How do you make sure they don't, pull in opposite directions?
That's where meta-learning comes in. It's the framework they use to handle this bi-level problem.
Meta-learning. I've heard that term, like learning to learn, right?
Precisely. Instead of just training a model on one specific task, meta-learning tries to learn general knowledge from a distribution of tasks. It's perfect for this because it lets the system learn how to generalize from lots of examples.
Which then helps it adapt faster to new user prompts and new tasks.
Exactly. It facilitates that rapid adaptation we're looking for, like a student who learns how to study effectively by tackling different subjects, making them better prepared for a brand new subject later on.
Okay, so meta-learning is the strategy. How did the researchers actually implement this? What's the mechanism?
They developed a specific framework they call Meta-Level System Prompt Optimizer, or MetaSPO for short, METASPO.
MetaSPO, got it.
And this MetaSPO framework basically runs on two loops. There's an inner loop for the user prompt optimization and an outer loop for the system prompt optimization. It's how these two loops work together, guided by meta-learning, that gets you the results.
Two loops. Okay, let's break those down. The inner loop first, what's happening there? How does it optimize the user prompts?
Right, so the inner loop focuses on one specific task at a time. It takes that task and tries to make the user prompt for it better and better, iteratively.
Iteratively.
Well, MetaSPO is flexible. You can plug in different optimization techniques. A key one they used works by looking at the mistakes the LLM makes. First, it tests the current user prompt on some examples for that task.
Okay, find where it fails.
Exactly. Identify the incorrect answers. Then comes a really neat part. Failure analysis. It actually prompts the LLM with the current user prompt and the examples it got wrong, essentially asking, why did you mess this up?
So it's asking the LLM to self-critique its reasoning based on the instructions.
Pretty much. It helps figure out where the prompt might be confusing or lacking. Based on that analysis, the framework generates some new candidate user prompts potential improvements.
Trying to fix the identified issues.
Right. And finally, it evaluates these new candidates, along with the previous ones, on the task examples and picks the best performing ones to carry forward. It's a cycle of test, analyze failure, generate fixes, evaluate.
That sounds like a solid process for refining a specific user prompt. Very targeted.
Hmm.
So what about the outer loop then? How does that work and how does it optimize the system prompt for that broader goal?
The outer loop has a similar sort of structure, but a much broader goal. Instead of one task, it's looking across a whole distribution of tasks.
Okay, so it's aggregating information.
Yes. It starts by measuring how well the current system prompt is doing across several different tasks. And importantly, for each task, it uses the best user prompt that the inner loop found for that specific task.
Right, using the optimized tools for each job.
Then it gathers up all the incorrect responses the LLM made across all those different tasks using that current system prompt. This collection of errors is then used to analyze the system prompt itself.
So analyzing the system prompt based on failures across multiple areas.
Exactly. Similar to the inner loop's failure analysis, but now looking for patterns of failure driven by the overarching system instructions. Based on that analysis, it generates multiple candidate system prompts, aiming to fix those cross-task weaknesses.
Trying to find a system prompt that avoids those common pitfalls.
Precisely. And finally, these candidate system prompts are evaluated across the whole set of tasks again, using the best corresponding user prompts for each, and the top performing system prompts are selected. This pushes the whole system towards better generalization.
Wow, okay, so the inner loop sharpens the tools for each specific job, and the outer loop looks at how all those jobs went and refines the overall workshop instruction, so to speak.
That's a fantastic way to put it. The system prompt is essentially learning from the collective experience of tackling diverse problems, each with its own optimized approach.
It's quite an elegant setup.
Yeah.
So how did they test if this MetaSPO thing actually works in practice? What did the experiments look like?
They designed some pretty thorough experiments aiming to mimic real-world use cases. They focused on two main scenarios.
Yeah.
The first one they called unseen generalization. This is the tough one. They took a system prompt optimized by MetaSPO and just used it directly on totally new tasks it had never seen during the optimization phase.
And no tweaking of the user prompts for those new tasks.
Nope, no extra help. This really tests if the optimized system prompt itself carries that generalizable power.
That definitely sounds like a strong test. What was the second scenario?
The second was test time adaptation. Here, they still use the MetaSPO optimized system prompt on a new task, keeping it fixed. But they allowed a little bit of optimization for the user prompt specifically for that new task, using just a few examples.
So seeing if the optimized system prompt gives you a better starting point for quickly tuning up for a new task.
Exactly. Does it provide a good foundation that makes further task-specific tuning easier or more effective?
Makes sense. And what kind of data did they throw at it for these tests? What tasks?
Oh, they used a really diverse set. 14 unseen tasks spread across 5 broad domains: medical, review analysis, reasoning, grounding, and safety. A real mix.
Can you give some examples?
Sure. For medical, think of datasets like MetaMCQA medical questions. For review analysis, they used Amazon product reviews. Reasoning tasks came from places like Big Bench, which has tons of different logic and reasoning puzzles.
Yeah.
Grounding involved things like Squad Stanford question answering dataset and natural questions, where the answers have to be based strictly on provided text. And safety used datasets like tweet eval for identifying harmful content. So yeah, a really broad evaluation.
That is a seriously diverse lineup. You're testing it on medical knowledge, sentiment logic, reading comprehension, safety.
Hmm.
Impressive. And who are they comparing MetaSPO against? What were the baselines?
Good question. They had several key comparisons. First, a simple default system prompt, just you are a helpful assistant, kind of the standard basic instruction,
The vanilla version.
pretty much. Then chain of thought, where they added let's think step by step to the prompt, a common technique to boost reasoning.
Right, seen that one a lot.
They also included a service prompt, which was actually a commercial prompt from a company called Haskell, so representing a high-quality, human-crafted prompt used in the real world.
Okay, comparing against professional prompt engineering.
Exactly. And finally, they compared it against SPRIG, SPRIG, which stands for System Prompt Optimization using genetic algorithms. This is another automated method for system prompt optimization, but it doesn't use meta learning, so a direct competitor in terms of the goal, but a different approach.
Got it. Default, chain of thought, a commercial prompt, and another automated technique in the underlying LLM for most of this.
The main workhorse was Llama 3.2, the 3 billion parameter version. And for the actual prompt optimizer within MetaSPO, the part doing the failure analysis and generation, they mostly used GPT-4o Mini.
Okay, setup clear. Let's get to the results. How did MetaSPO do in that first scenario, unseen generalization, when thrown at new tasks cold?
The results there were really quite strong. MetaSPO consistently outperformed all the baselines across those 14 unseen tasks and the 5 domains. It really highlighted the ability of these optimized system prompts to generalize well.
Consistently better. That's significant.
Yeah. And they dug into it further. They found that something like 85% of the user prompts they tested performed better when paired with the MetaSPO system prompt compared to the simple helpful assistant default.
Wow, 85%. So it's providing a tangible benefit for the vast majority of user instructions on these new tasks.
It really suggests it's providing fundamentally better guidance, enabling the LLM to tackle new stuff more effectively.
Very compelling. What about the test time adaptation scenario, where they allowed a bit of user prompt tuning on the new tasks?
MetaSPO came out on top there too. It consistently beat the other methods, which suggests that the system prompts it generates aren't just good on their own, they also provide a superior starting point, a better foundation for quickly optimizing user prompts for new tasks.
So it helps you get better results faster when you encounter a new problem.
Exactly. It's like starting with a really well-prepped canvas makes the final painting easier and better.
Those are solid performance results. Did they look into why it might be working so well? Like, did it matter how similar the new tasks were to the ones MetaSPO was trained on?
Yes, they did analyze that. They hypothesized that, if the new test tasks were more similar to the source tasks used during the meta-learning, the benefit would be bigger.
Makes intuitive sense. How did they measure similarity?
They used a technique called bag of words rank correlation, basically looking at how similar the vocabulary and word patterns are between the task examples, and they found a clear, positive correlation.
So more similar tasks meant bigger improvements.
Yep. A Pearson correlation of plus 0.56, technically speaking. It suggests that the closer the new task is, linguistically, to what it trained on, the more boost you get from the MetaSPO prompt compared to the default.
Okay, that fits with how we generally think about transfer learning. But did it only work for similar tasks? What if the tasks were really different?
But that's the interesting part. While the gains were bigger for similar tasks, MetaSPO still showed noticeable improvements even when the target tasks were quite dissimilar to the training ones.
Oh, really? So it wasn't just memorizing stuff from the training tasks.
It seems not. It suggests MetaSPO is actually learning more fundamental, generalizable ways to instruct the LLM that are helpful even in quite different situations. That's a really key finding for true generalization.
That is key. It hints at something more robust than just pattern matching. What about crossing domains entirely, like training on reviews and reasoning, but testing on medical questions?
They specifically tested that too, cross-domain generalization. They trained MetaSPO on tasks from, say, 3 domains, and then tested it on tasks from completely different domains it hadn't seen.
And how did it do there? That sounds like a major leap.
It still held up. MetaSPO consistently outperformed the baselines, even in this challenging cross-domain setup. And they also found that the best cross-domain performance usually came when they trained it on a diverse set of 3 different source domains.
So diversity in training helps it make those bigger leaps across domains.
Seems so. Variety during the meta-learning phase appears crucial for building that robust, widely applicable system guidance.
Okay, so it Performs well, it generalizes well, even across domains.
Yeah.
What about efficiency? Does it take a lot of effort or data to get these gains?
That was another thing they looked at closely. They compared how quickly MetaSPO could reach the same performance level as the default prompt during that test time adaptation phase.
Was it faster?
Significantly faster and more efficient. They found MetaSPO could hit the default prompt's final performance level using about 80% fewer optimization steps.
80% fewer steps. Wow.
And using about 75% less data for that adaptation phase.
Okay, that's a huge saving. So potentially really valuable if you don't have tons of data or compute time for every new task.
Exactly. It suggests these optimized system prompts can make deploying LLMs on new tasks much more practical in resource-constrained situations.
Did the number of tasks used during the initial MetaSPO training matter much? Like, is training on one task enough, or do you need lots?
They check that too, varying the number of source tasks from just 1 up to 6. The general finding was, yes, using more source tasks generally boosted MetaSPO's performance and made the results more stable.
More training data is usually better, right?
Usually, yeah. But the amount of improvement varied. For instance, in review analysis where the tasks were maybe more similar to each other, going from 1 to 6 source tasks gave a big jump, like 17% improvement.
Okay.
Whereas in reasoning, the improvement was smaller, though still positive. It reinforces that idea. A diverse set of training tasks helps, and it helps even more if those tasks have some resemblance to what you'll encounter later.
Makes sense. Now, thinking about how we feed prompts to LLMs,
Yeah.
usually there's a specific slot for the system prompt and another for the user prompt. Did they test if keeping them separate actually matters?
They did look into that. They tried 2 ways. 1, keeping system and user prompts separate, assigned to their proper roles the standard way.
Okay.
2, they just smushed the optimized system prompt and the optimized user prompt together into one big user prompt.
And did it make a difference?
Generally, yes. Keeping them separate led to better performance in most domains. The exception was reasoning, interestingly. But overall, it suggests these LLMs really are trained to treat system and user instructions differently.
So respecting that structure helps the model perform better.
It seems that way. The architecture and how it was trained expect those distinct roles and performance benefits when you stick to that.
Interesting. Did they try to peek inside the LLM's head, so to speak, to see if it was actually paying more attention to these MetaSPO prompts?
They did. They looked at attention scores, basically, how much computational focus the model puts on different parts of the input. They compared attention on the system prompt versus the user prompt for MetaSPO versus the baselines.
And what did they find? More attention on the MetaSPO system prompts.
Consistently, yes. Across all the domains, the LLMs paid significantly more attention to the MetaSPO optimized system prompts compared to the baseline ones.
So that suggests the MetaSPO prompts are actually providing more meaningful guidance that the model finds useful.
That's the interpretation, yeah. It's empirical evidence that these prompts aren't just different, they're more impactful in guiding the model's processing.
Fascinating. Okay, one more thing on generalization. LLMs are evolving so fast. Does a system prompt optimized using MetaSPO on one model, like Llama 3.2, work if you switch to a different model?
Excellent question, and yes, they tested that as well. They took the prompts optimized primarily on Llama 3.2 and tried them with other models, Llama 3.1, the 8B version, Quinn 2.5, 7B, and even GPT-4 Mini.
And how did that go? Did the prompts transfer?
They did remarkably well. The MetaSPO prompts showed strong performance and generalization even on these different models. They even did what they called class model generalization optimized on Llama 3.2, test directly on another model with 0 changes, and it still worked robustly.
Wow. So the principles MetaSPO learns for writing good system prompts aren't just tied to one specific LLM architecture.
It seems they're more broadly applicable, which is really significant for the practical utility of this approach.
Yeah.
It's not brittle.
That's huge.
Yeah.
Lastly, you mentioned MetaSPO as a framework, and they use specific techniques inside it. Did they try swapping those out, like using different ways to do the inner and outer loop optimizations?
Yes, they explored variants. They tried plugging in other known prompt optimization methods like APE, Automatic Prompt Engineer, or EVO, using evolutionary algorithms, into the loops.
And did those variants work?
They did. Those versions of MetaSPO using different internal engines still managed to outperform the baseline methods, so the framework itself seems flexible.
But was the original setup the best?
Generally, yes. The full MetaSPO, with both the inner loop optimizing user prompts and the outer loop optimizing the system prompt working together, tended to give the best overall performance.
So that synergy between the two loops is important.
It appears to be crucial. They also tested just using the outer loop, system prompt optimization, without the inner loop, user prompt optimization. And while it was okay, maybe comparable to baselines, it wasn't as strong as the full two-loop system. That interaction really adds value.
Okay, that was incredibly thorough. They seem to have covered a lot of ground. So, wrapping up the findings, what would you say is the main significance of this research overall?
I think the biggest thing is that it really shines a spotlight on system prompts, an area that's been relatively neglected compared to user prompts. It shows there's huge potential there for making LLMs more robust and adaptable.
Right, moving beyond task-specific tweaks.
Exactly. By framing it as this bi-level optimization problem and bringing in meta-learning with the MetaSPO framework, they've shown a practical, automated way to create these powerful general-purpose system prompts. Prompts that work well across different inputs and even transfer to totally new tasks and domains.
It feels like a foundational step towards more capable and versatile AI.
I think so. It could really change how efficiently we can deploy LLMs for diverse real-world applications, getting us closer to leveraging their full capabilities.
So for someone listening, what's the key message they should take away from this deep dive?
The core takeaway is that meta-learning is a really powerful tool for this specific challenge of optimizing system prompts. The MetaSPO approach demonstrates convincingly that you can automatically learn system-level guidance that generalizes incredibly well.
Learning from diverse tasks to improve the fundamental instructions.
Precisely. And doing that leads to real, measurable improvements in both performance and efficiency when dealing with new situations.
This has been absolutely fascinating, really digging into how we can give better foundational instructions to these incredibly complex models. It definitely sparks some thoughts about the future.
For sure.
And maybe here's a final thought for you, our listener, to mull over. With these kinds of advances in automatically optimizing prompts, especially these core system prompts, how might that fundamentally change how we interact with LLMs down the road?
Hmm.
Could we be moving towards an era where we have highly specialized AI assistants for almost anything, science, art, education, personal tasks, all built on foundations that were automatically discovered and optimized for adaptability? It's certainly a compelling future to think about.